This question is about atomic structure and mass spectrometry. Give the full electron configuration of Br. So the first thing you'll need to do is go to the periodic table, locate bromine. So this is going to be a long one because bromine is element number 35 in the periodic table. If you look at its location in the periodic table, you can see that it is in group 7, so the fifth column along in the P block. It's in the fourth row down, so it's going to end 4p5 because of its location, but we've got to go all the way through all of the electron configuration to that point. So through the first shell, fill it up, into the second shell, past the S block, past the P block, filling them up, into the third shell, past the S block, past the P block. Leave a finger space because we then jump into the fourth shell, fill 4s, we go back and we fill 3d across the transition metals. Then we start filling 4p, and we've got, remember, the 5. If you add up the electrons in that now, you should see that that adds up to 35. So the first up to 2p6 is 10, then there's 18, and then another 10, 28, 30 with the 4s2, 35. A sample of bromine Br2 is analysed using a mass spectrometer, using electron impact ionisation, give an equation including state symbols. So we're taking our bromine sample as a gas, we're firing high energy electrons at it, and they're going to knock off an electron. So it becomes a Br2 with a 1+ charge gas and an electron. High energy electrons knock off an electron. The bromine exists as 2 isotopes which are in equal abundance. Figure 1 shows an incomplete mass spectrum for this sample of bromine. So we've got to figure out the possibilities of the different ways that we can have this. So there's a number of ways you could do this. You might want to do a probability tree, but we've got 2 isotopes, 79 and 81. If you combine 79 with 79, you get 158. If you combine 79 with 81, you get 160. 81 with 79, you get 160. And 2 81s, you get 162. So you can see that in total, there is 4 different possible answers, but 2 of them add up to the same number. This would accumulate our entire 100%. So each one of these little squares is worth 25%. So at 162, we've got another 25% because there was just 1 square for that. But at 160, we can see that there was 2 ways of making 160. So 50% of all of your sample was in the 160 mass number range. State how the detector enables the relative abundance of each isotope to be determined. Oh, I've missed out part of that question, I think, because I haven't added the labels to the axes, so I should do that. This is m/z, mass to charge ratio. And this is, given that they go up to 100, this is percentage abundance. State how the detector enables the relative abundance. Well, the abundance is proportional to the current generated let's put the size just to be clear. When the ions gain electrons at the detector.